All right, guys, 2019 free response question number 3. So they've given you a graph right here, and that is the graph of f of x. Always a good idea to make a note right here about what it is you're looking at the graph of. Sometimes this might be f prime, this might be g. So they tell you f right here. We've got it defined on a closed interval. We've got two line segments, so linear functions here and here. And then they don't want to leave this up to an assumption. They tell you that this piece right here on the right is a quarter circle centered at the point 5, 3. So that's worth knowing. And then a lot of times they sneak relevant information here at the end of the text of a problem. They're giving you a point right here of 3, comma, 3 minus the square root of 5. Now that's on the graph of f, so that's what we're dealing with right here. If you remember that the square root of 5 is a little bit more than 2, you know that this y value then of 3 minus root 5 should be a little bit less than 1, and sure enough that matches up with what we think we know right about there. So not quite sure yet how that's going to be relevant, but I'm sure it'll matter at some point here. The first part of this problem here, they give you a value of a definite integral here from -6 to 5, and you'll notice that goes beyond this graph to the left out here, so it gives you some information that the graph doesn't show, and it tells you the value of that definite integral is 7. So we're supposed to come up with the value of the integral just from from -6 to -2 and show work that leads to it. So let's take a look at what's going on. So what we used here was the additivity property for definite integrals, that the overall value of the integral starting at -6 and ending at 5 of f of x can be broken up into an integral that goes from -6 to -2 plus an integral from -2 to -5. If you're wondering where the -2 came from, well, that's where we actually started having some information about this function here. So really the question mark is what was happening from -6 to -2, and again, that's what they were asking us to find right here. So that's why we chose to split this one up at -2. 3 parts to this equation, and they tell you in the problem that that first integral right there from -6 to 5 has a value of 7. So that's simply where that comes from. This is the integral we're trying to solve for, so it's not surprising that we don't know it. But then this integral right here, the value of the integral from -2 to 5 of this function, is what we had to figure out. So looking back at the graph, they cut us a couple of breaks right here. Starting at -2, we have a triangular region right here above the x-axis, but then ending at 0, there's another triangular region that's identical to it, but below the x-axis. So we know that the integral here from -2 to 0, it's just going to be 0 because these two regions are going to cancel each other out, one being above and an identical congruent region being below the x-axis. The same exact thing happens starting at 0 and ending at 1 right here. We've got this little skinny triangular region below the x-axis and an identical one right here above the x-axis. So the integral here from -2 to 1 is going to be completely 0. That just leaves us then really worrying about the integral here that starts right here at 1 and ends over here at 5. So to do that, what I probably would think about doing is cutting this up into a trapezoid right over here, and then the remnants of the quarter circle right there. So for the trapezoid there, everybody, 1/2 times the height of 1 times bases of 1 and 3 is going to get you an area for that trapezoid right there of 2 square units. And then when it comes to this region right over here, probably helpful to think about this square right here going around the entire thing. Now the area of that square right there is going to be 9. And that is part of what we don't want here. What we want is everything that's in that square but's not within that quarter circle. So we're going to subtract from that 9 the area of the quarter circle, which is going to be a 1/4 pi times a radius of 3 squared. So putting all that together, this becomes a 9/4 pi. So that's a 9 minus 9/4 pi. That is the area of this shaded region right over here. So when we put together this 2 here for the trapezoid and the 9 minus the 9/4 pi for that little sliver right over there, we get an area here for that integral of, eventually right over here, and I never actually added those together, the 9 and the 2 are going to get us the 11 right there. and there's the minus 9/4 pi that we had. So putting all of that together now, the integral, which I left part of that out here, we were trying to solve for, would start with this 7 here, and we would subtract all of this from it. So the 9 and the 2 add up to make an 11. Subtract that from the other side, and the 7 minus 11 is going to give you this -4 here. Oops. And then this negative 9/4 pi that was on the right, we're going to bring that to the left where it becomes positive. And that's the answer to part A, 9/4 pi minus 4. Okay, second question now is asking us to evaluate a definite integral from 3 to 5 of 2f prime of x plus 4 dx. So, being asked to evaluate this integral right here, we're going to go ahead and apply some of those properties of definite integrals that we learned way back in the day early in chapter 5. And we're going to do the sum property. The integral of this sum is the integral of the first term plus the integral of the second term. And at the same time, we're going to use the constant multiple rule to pull this 2 out in front of the first integral. So that gets us the integral from 3 to 5 of f prime of x dx plus an integral from 3 to 5 of 4 dx. This integral right here should strike you guys as something familiar. We're doing a definite integral of a derivative, f prime. So we would anti-differentiate our integrand, and the antiderivative of f prime is going to be just f. So, using fundamental theorem of Calc part 1, this integral becomes f of 5 minus f of 3. And over here on the other side, don't forget to anti-differentiate the constant with respect to x, which is going to give you a 4x evaluated from 5 to 3. Now the values of f of 5 and f of 3 come directly from the graph that we were given. Remember, this is the graph of f. So the value of f of 5 right here is going to be 0, and the value of f of 3 is right there, and that's the weird value that they gave us here a while ago. So like I said, that ends up being relevant at some point in the problem. They usually don't give you extra information. Okay, so with all that in mind right here, the f of 5 we said was 0. The f of 3 was the quantity 3 minus the square root of 5. That 4x evaluated from 5 to 3. Remember, guys, this is really just a rectangle right here. The 4 times 5 is 20, the 4 times 3 is 12, and the 20 minus 12 gets you this 8 here. So that is a -3 that's going to get multiplied by a 2 to make a -6. That -6 combines with this 8 to give us a 2. And then the 2 is going to get multiplied by the opposite of -√5, and that's where the plus 2√5 comes from. Nothing more you can do with it than that, so that's the answer for part B. Part C, the function is g is given as this one right here. And not anything surprising here. You will see stuff like this from time to time where one function is defined as the definite integral of another function, and your variable of the function, in this case, of course, being x, very often ends up being the upper limit of integration in that second function. And they want us to find an absolute maximum value on that spot there. So the first thing I'm hoping you guys would remember at a case like this is that when you see a phrase about an absolute max or an absolute min, there are only two places that an absolute max or min can occur. They can occur at endpoints, and they can occur at critical points. Endpoints are easy to spot right here, -2 and 5. And critical points occur anywhere that the derivative of your function is equal to 0 or is undefined. But let's not be vague right here. We're trying to find the absolute maximum value of g. So for critical points, we need the derivative of g, or g prime of x, in order to find those spots. So let's see what we did over here for part C. Okay, so with the original function, g of x was given to us and defined thusly. Its endpoints we knew were at -2 and 5. The AP graders are going to want to make sure that you know to check these points, even if they don't end up giving you the correct answer there. So those are the endpoints. And as far as critical points, we had to take the derivative of g. So the derivative of a definite integral with a constant for the lower limit and a variable for the upper limit, all we do then is replace this variable t here with this variable up on top. So the f of t simply becomes an f of x. That right there, everybody, is fundamental theorem of Calc part 2, which is another one that can be easy to forget if we haven't studied it in a while. And so those things happen at 3 spots right here, guys. F of x is equal to 0, and if we go back and look at the graph of f, which we're looking at here, equals 0, right here at -1, right here at a positive 1/2, which I know because this is a linear function, and again, right over here at 5. So that got us 3 potential spots right there for critical points: -1, 1/2, and 5. I should be clear, what I said there was technically wrong. These are critical points right here. Anywhere that your derivative is equal to 0. They are potential extreme values, either a max or a min, and we'll find that out in a second. There are no spots where our derivative, f of x, is undefined on this interval, so we don't have to worry about that. So we had, let's see, 1 and 2 endpoints right there, and then 1, 2, and technically a third critical point, but this third critical point was the same as one of our endpoints right there. So we really ended up with 4 potential spots where we had to look to find an extreme value. And so to do that, you just got to make a table right here and show what's going on right here. So we had to test the value of g of x at these 4 x values that we came up with. Okay? So the first one was easy. G was an integral from -2 to x, and if x is -2, that means we're doing an integral from -2 to -2, which is automatically going to be 0. The second one here was maybe a little bit tricky. We were doing an integral here starting at -2 and ending here at -1. And I think I might have made a mistake in this one right here. Let's talk about why. The thing I'm always concerned about on a problem like this is, are the limits of integration ever going to be backwards? And when I did this a few minutes ago, I think that I was thinking that they were, but now that I look at it again, they're not. -2 on the bottom is clearly less than the -1 on top. So if we go back to the graph itself and we looked at the area between the curve and the x-axis from -2 to -1, we've got a triangle. 1/2 times a base of 1 times a height of 1 gets us an area of 1/2. It's above the x-axis, so it would normally be positive, and the limits here from -2 on the bottom to -1 on top are in the correct order, so that actually should be a positive 1/2 there for that value. Okay, moving on to a 1/2 right now. We can go back to something we talked about a second ago. The integral from -2 to 1/2. Well, again, this region here and this region here completely wipe each other out. So we're really just interested in this area right here, which is 1/2 times a base of 1/2 times a height of 1. So the area of that triangle is 1/4. And since it's below the x-axis, but the limits from -2 to 1/2 are in the correct order, that integral is going to end up being a -1/4. And the last one, the toughest one here, was the integral from -2 to 5, but that is information that we came up with back here in part A. Everything we needed was this integral right here from -2 to 5 of f of x dx. So that's where I got to right here, and I never quite put it all together, but the 9 and the 2 was an 11, and then minus that 9/4 pi. So back to our table here, that's where we came up with the 11 minus the 9/4 pi. So armed with those 4 values of g right here, we're now able to find that the absolute, and I read that wrong, I initially thought minimum, the absolute maximum value of this function comes at the highest right there of those 4 values. And I don't love problems like this where you don't have a calculator and they're asking you to come up with an approximation for an irrational number, but we should be able to tell whether this number right here is more or less than 1/2, the only other positive number that we had. Well, okay, guys, 9/4 is 2 1/4. 2 1/4 times pi, which is a little bit more than 3, is probably going to put us somewhere in the neighborhood of 8 or so, and 11 minus 8 is going to be 3. So this value right here ends up being the absolute maximum value. And note the way that we answered the question. They didn't say where does the absolute maximum occur, so I'm not telling them x equals 5. They just asked for the absolute maximum value of g, which means they really want the y value, and that's what we came up with right here. And the last question, D, this one surprised me a little bit because, I don't know if you guys thought the same thing, as soon as I looked at D, I thought I knew directly what it was that they wanted us to do, and it turns out I was wrong. When I looked at it here as a limit question here on a free response question, I thought for sure this was going to be a L'Hopital's rule problem. But good thing that I didn't make an assumption right here. You should never assume that L'Hopital's necessarily works without trying direct substitution first and making sure that you don't get either 0 over 0 or infinity over infinity. If one of those two cases happens, that's when you want to do L'Hopital's rule. So I decided to check that real quick and see what would happen here in part D. So let's take a look at that. Okay, so for part D, this is the limit we were looking at right here, 10 to the x minus 3f prime of x over f of x minus the arctangent of x. So I didn't even put an equal sign because I thought this was not going to work, but let's see what happened then. That numerator became 10 to the first power, just 10, minus 3 times f prime of 1. Okay, going back to the graph right here, f prime of 1 would be the slope of the tangent right here, and since we have a linear function at that spot, we can see that the rise is 2 and the run is 1, so the slope of f at 1 is 2. So that is where this 2 right here came from. Then on the bottom, f of x would become f of 1. Looking back at the graph, f of 1 is equal to 1. So that's where this came from, minus the arctangent of 1. Had nothing to do with the graph right here, but the angle between negative pi over 2 and positive pi over 2 with a tangent value of 1 is pi over 4. So at this point I said, oh, okay. And that's when I started to realize this was not L'Hopital's. So the numerator is a 10 minus 6, which gets us a 4. And I did something they didn't bother to do. I made that 1 into a 4 over 4. Put these two fractions together to make a 4 minus pi over 4. And then remember that the denominator of your denominator actually ends up going into the numerator as well. And I came up with a 16 over a 4 minus pi. When I went and checked their solution, I saw that they didn't do quite as much grunt work as I did. They left that numerator as a 4, and they left the denominator as it was of 1 minus pi over 4. So both of these answers right here are perfectly correct. Of course, I like mine better, but that's the one that they came up with.